Ladies and gentlemen, can I have your attention please? My name's Sandy Chidup and I'm the head of the School of Geosciences, and it's my pleasure to welcome you to the third in this year's Our Changing World lecture series. And there's a number of reasons why today's talk on a short or brief history of CO2, carbon dioxide, is particularly appropriate. First of all, it was in Edinburgh that Joseph Black actually discovered CO2, carbon dioxide, called it fixed air, in about the 1750s. So we've got a kind of geographical reference there. It's also very timely to be talking about atmospheric CO2 because the Intergovernmental Panel on Climate Change has just released its latest report, and that has confirmed that carbon dioxide in the atmosphere has demonstrably changed climate already. It's changed sea level already, and it's likely to cause significant future climate change and change in extremes. So it's a great pleasure to welcome our speaker who's going to tell us some more about this, and it's Professor Paul Palmer, my colleague in geosciences. And Paul's a physicist who's got interested in how he can use his physics to understand how the Earth works. He started in Bristol and then Oxford and moved to Harvard, back to Leeds, and then to Edinburgh. And he's now a professor of quantitative Earth observation with us in the School of Geosciences. His particular interest is in how you use information from satellites and modeling to understand the sources and sinks of gases in the atmosphere, in particular some of these reactive gases, the important gases like the greenhouse gases, including CO2. And in this he's become a renowned world leader. He's won several very prestigious awards from the Russian Academy of Science, the Zeldovich Medal, the Philip Leverhulme Prize, the very distinguished Royal Society Wolfson Research Merit Award. And so without any further ado, I think I'll just pass straight over to Paul to give us a brief history.
Great, thank you very much for the introduction. Good evening. So, what am I going to talk about? I'm going to talk about atmospheric CO2, brief history. Now, the reason why I'm doing this is when people normally talk about climate change, they assume the importance of CO2, they sort of brush it aside and assume that we already know the climatic importance of carbon dioxide. But there's a great story behind this, and it goes on for about 200 years. So I thought I'd introduce at least some of the scientific pioneers and introduce some of the puzzles that have led up to our current understanding of carbon dioxide and its climatic importance. So as Sandy said, I don't just work on CO2, and if you want to know more, you can go to my website, or you can click on the quick recognition code up there at the top. So this is, out of all the slides I'm going to show you today, this is probably the one you'll recognize. This is the CO2 at Mauna Loa's in Hawaii in the middle of the Pacific. And what I'm showing you here is CO2 in parts per million. We'll get to that in a minute, but basically this is CO2 from 320 to almost 400, it's now past 400. As a function of time. Now, CO2 measurements at this site started in the late 50s with Charles Keeling, and sometimes this curve is called the Keeling curve. It's one of the most iconic curves of the 20th century, and what it shows is that there's this increase in CO2 through the 20th century into the 21st century. What the red line is showing is the data, and what it's showing is this like wiggly line. And that wiggly line tells us something about the land biosphere, trees and vegetation, and it tracks the respiration and photosynthesis throughout the year. So it's a repeatable curve. And we'll talk about the importance and how to tease apart some of that information in this data later on in the lecture. Superimposed on that wiggly line is this ramp up of CO2 in the atmosphere, and we're sure that this is due to fossil fuel combustion. The accumulation of CO2 in the atmosphere is the CO2. So we'll talk about the role of fossil fuel and the terrestrial biosphere later on. So in this talk, we're going to pose four questions. We'll have four questions. The first one is the one that people generally assume is already known. So we're going to figure out how we know the climatic importance of CO2. And this is the story I was telling you about the scientific pioneers. What determines atmospheric CO2? So we're talking about the sources and sinks. So that's already jargon, isn't it? So sources are the emissions into the atmosphere, usually from the surface to the atmosphere, and sinks are processes which take CO2 from the atmosphere into the ocean or into the land, okay? We also talk about fluxes, so you have to forgive me. Sometimes I say fluxes, sometimes I talk about source and say fluxes is the net source, okay? So you have a positive flux, that means you've got a net emission into the atmosphere, and if you have a negative flux, that means you have a net uptake of CO2 from the atmosphere. We'll talk briefly about the future of atmospheric CO2. There's not a huge amount I can say about this, but I'll tell you about what people think, or at least give you the range of CO2 concentrations will increase in the 21st century. And then I'll finish off by showing you how we can use atmospheric CO2 to help test mitigation strategies. And I'll give you an example of a new project that Edinburgh I'm leading, to quantify the greenhouse gas budget of the UK. So let's just start with trying to get you up to speed about just what's all on the same page. So CO2, so if you have a volume of air, so you have this whole lecture theatre is full of air, hopefully. Most of it is nitrogen, then oxygen, then argon, and then the fraction of percent that's left of that, a small amount of it is CO2. So about 0.4%, it's probably a bit higher in here actually, but 0.4% of the air in this lecture theatre is CO2. Okay, so it's very dilute, very small amount. And so we talk about atmospheric concentrations in terms of parts per million. And we saw already that it's about 300 to 400 ppm. And you'll see that on many of the graphs. That's one of the units I'll show in many of the graphs, a ppm, so remember that. There'll be another unit, but I'll introduce that in a minute. The size of the CO2 is a triatomic molecule. You'll see there's a carbon in the middle, double bonds attaching to the oxygen. This is about a trillionth of a meter. So it's small, dilute, and yet exerts a tremendous influence on the evolution of Earth's climate. I also wanted to just touch on the fact that this greenhouse gas effect. I just want to make sure, again, we're on the same page about, because this plays an important role. CO2, this is the Earth. So we have space up here in the grey, we have the atmosphere in blue, and then the brown surface, Earth's land ocean surface. We get energy from the sun. Sun's hot, very hot, and it's emitting radiation at very high energies. Most of that radiation passes through the atmosphere. Some of it heats up the atmosphere, but most of it passes through, you'll see. All these numbers you'll see are in terms of watts per meter squared, and watts a measure of the rate of energy transfer. The Earth is warmed up by the sun, and then it emits its own radiation in terms of thermal radiation. So you'll see that this brown line is the thermal radiation from the Earth. And this is the kind of energies that the greenhouse gases like. This is the energies that they start getting really excited about, and they start moving around. And we'll have a little movie here in a moment about how they move around. And this leads to the heating of the atmosphere and the energy depth. And this heats up the surface. What I wanted to make sure that you knew was that the greenhouse gas effect is a natural effect. It's something that we need to have on Earth, otherwise we're 30 degrees cooler. Okay? What we're concerned about is the enhanced greenhouse gas effect, the elevation of CO2 above ambient conditions, which increases this feedback between the atmosphere heating the land emitting radiation, greenhouse gases absorbing that radiation, warming up the atmosphere, and so forth. Okay. So these are, the sound was, okay, these are, well, the students put together for me, and I thought I'd turn the sound off actually, but this is one of three movements. I'm going to have to turn it. The sound threw me there for a minute. I was going to do that at the end, but okay, so let's do that again. Okay, so this is the bend molecule, bend mode. This is one of three, so they're moving like this. They're also moving like this. Okay. The other, so this is relevant to infrared radiation in the atmosphere. The second one is this asymmetric mode. Okay, I don't know what to do with this on my hand, but they have this movement here. And the important thing is this is also relevant for the greenhouse gas effect. There's a charge separation for the physicists in the crowd. It means it has a dipole moment, which means it absorbs and emits radiation. And there's a third mode, which is a symmetric mode. And this doesn't radiate, but I didn't have the heart to tell them that this one didn't radiate. But it's important that it was just for completeness sake, there was a third mode here. So The upshot of this, so you emit radiation, the radiation warms the Earth's surface. And so where does CO2 stand in all the other effects? So the way that climate scientists, the metric they use is something called radiative forcing. And this is what I've stolen from the latest IPCC assessment report, which just came out last week or the week before. And what this shows is the radiative forcing. The radiative forcing is a measure of the potency of anything to increase surface temperature. I won't go into the details, but this is essentially what it is. So we've got well-mixed greenhouse gases, short-lived gases, aerosols, the particles, we've got clouds, and then a whole bunch of other things. So when there's a positive radiative forcing, that leads to a surface warming. So if you change CO2, that's going to lead to a surface warming. And anything that, if it's negative, that means you perturb it, it effectively decreases. It cools the Earth's surface. And you can see CO2 is standing there proudly at the top, dominant in its impact on the Earth's surface. So that's why we're really interested in it. Okay, so now we're up to speed. So now the story can begin, and the story begins kind of where Sandy mentioned. We start in the 18th century with Joseph Black. Now he was a professor of chemistry here in Edinburgh University, and this was the time of the Scottish Enlightenment. So there's a lot of activity going on a whole range of subjects. So, and there was a lot of freedom to just throw around. There were no research councils. They got to play with whatever they wanted to do without any constraints at all. And what he did, one of the things he did was to play with limestone. And he heated up limestone, and he identified something called fixed air, which is CO2. Now CO2, fixed air was heavier than air, and it didn't support life, animal life. It didn't support flame. And he also, so this was a very comprehensive study. So eventually he made these connections between CO2 and the animal respiration and also microbial fermentation. So he did a really big study, and he was the first person to really go to town on understanding, identifying CO2 and where it was coming from. The second key person, I should say this is not a comprehensive. These are the people I think made a really big impact and are worth mentioning. So there's a whole bunch of other people that I haven't mentioned. The second person is Joseph Furio, and you might know his name because some of the maths that you did at school features his name. So the Fourier series, Fourier transform, they all bear his name. At this point, we've increased the CO2 from 275 to 280 ppm. So this is 1824. And one of the things he was concerned about was looking at, he thought the distance away from the sun, the Earth's surface. If there was, the temperature of the Earth's surface is much warmer than it should be given the distance away we are from the sun. So we must think that the atmosphere is acting as some kind of insulator. So he was the first person to really think about this, the atmosphere as playing a key role in determining the Earth's atmosphere. And allegedly, I'm not sure about this, but allegedly he was the first person to coin the greenhouse, or the analogy between the atmosphere and a greenhouse. So this is the other thing I want to make sure that you understood. The greenhouse is a great teaching analogy, but in terms of scientific accuracy, it's not very accurate. So we have a greenhouse gas here that's transparent to sunlight. It's opaque to infrared radiation. So we heat the surface up, infrared radiation, it gets trapped in the greenhouse gas, in the greenhouse. In the real atmosphere, it's a lot more complicated, as you might imagine. And there's layers of greenhouse gases and particles and clouds that absorb the sun radiation and also the thermal radiation from the Earth's surface and heat up the atmosphere that way. So it isn't trapped. There's no trapping of the radiation in these layers. The other thing is that there's the role of convection. So many of the early calculations, we'll come to that, many of the early pioneers didn't have the scientific machinery to explore the role of convection in shuttling around heat and energy in the atmosphere. And they were limited to having radiation as the principal vehicle for shuttling this through the atmosphere. So the greenhouse gases analogy is very limited and largely inaccurate. So the third person is a guy called John Tindall. And by this time, CO2 in the atmosphere had increased by some 5 ppm, not very much. It's not going very much at all. Now, John Tindall, among other things, was the president of the Royal Institution in London. And he was a keen alpine climber. He was a very accomplished alpine climber, in fact. and he wrote books about glaciers. And so he had first-hand knowledge about how the glaciers waxed and waned. He knew that at some point the glaciers were moved tremendous amounts. And so much of what he was interested, he was motivated by the CO2 problem from the point of understanding how we got out of glacial periods into interglacial. How do we remove that huge amount of the ice volume from the Earth into this interglacial period? And he conducted a series of experiments in the lab, and he showed that water vapor and CO2 and a whole bunch of other gases had thermal absorption properties. So these gases, you can see he's starting to build up a picture here. So Joseph Furio made the connection with the atmosphere and some insulating property. John Tindall knows that there's some gases in the atmosphere and then shows that they have some thermal absorption properties of, well, we can see this building up. And we'll come back to the reason this is, each scientist is building on many other scientists' work, some, decades before, and in some cases a century before. There's a great movie here that describes the laboratory experiment that John Tindall did. It's based at the Science Museum in London, so they've got some of their original equipment still there. Then we moved to Arrhenius, and 1896, CO2 was still pretty low, it's 295. We're starting to get towards the Industrial Revolution. And again, he was really motivated by understanding the waxing and waning of these ice sheets and the temperatures. How are we getting out of these big glacial periods? And he was a bit more dismissive about the role of water vapor. John Tindall was more about the water vapor. Arrhenius he argued that water vapor was changing very quickly on a diurnal basis, and CO2, the sources that he was thinking about CO2 from volcanism, and the evolution of photosynthetic plants and mineral. Huge. I mean, so these changes of CO2 happened on sort of thousands of years, much more in line with the kind of temperature changes and the ice volume movements that you see in the ice ages. And here's the second Edinburgh connection here. So the first one was Joseph Black. This is the second one. He published one of his important papers in the London, Edinburgh, and Dublin Philosophical Magazine, so on the influence of carbonic acid, CO2 in the air upon the temperature of the ground. So I'll tell you how he did this. So he made this, what he did was to look at the atmosphere, moonlight through the atmosphere. And what he did was he borrowed some spectroscopy data from some guy, Sam Langley from the US. And as the light goes through the atmosphere, you're looking at it from the surface, you can see in the spectroscopy that there's certain features, the absorption lines, I don't need to go into these, but there's certain features in the atmospheric spectra which point to CO2. And by looking at different moon angles, he was able to find this relationship between temperature changes at the Earth and CO2 in the atmosphere. Great, so he's made that connection between surface temperature and CO2. So laboriously calculated, there's no computers in those days, so what he did was lots of pen and paper, and he calculated that halving CO2 in the atmosphere would lead to a 4 to 5 degree cooling. Okay, is this enough to get us into an ice age? So he went to one of his colleagues, allegedly, and this person was working on, as it just so happens, that he was working on looking at CO2 from factories. It's the Industrial Revolution. He was trying to figure out the importance of all these emissions into the atmosphere, and he suggested that the emissions of CO2 from these factories were comparable with the CO2 that you get from the terrestrial vegetation. Okay, so this is just as important. So then he seemed to switch he started looking at what would a doubling CO2 result in. And it turns out that it results in about a 5 to 6 degree warming. Okay, that's great. The point here is this is a very simplistic calculation, but it's incredibly pioneering, and in fact, it's not bad, actually. So this is another plot from the IPCC Assessment Report 5, and here we've got something called the equilibrium climate sensitivity, and it's essentially the calculation that Arrhenius did, but using large-scale computer models of the climate. This is the change in the global annual mean surface temperature following a doubling of atmospheric equivalent CO2. I'll just ignore the equivalent bit for now, but doubling the atmospheric CO2 concentration. The current, given this plot here, the current best estimate of this equilibrium climate sensitivity is between 1.5 and 4.5. And you can see this is a result of a whole range of different constraints, so instruments, climatological constraints, raw model output, paleoclimates, and combination of any of these. And this leads to this value given in Celsius. His value was 5 to 6 using pen and paper. Well, that's remarkable, isn't it? I mean, that's the huge amount of... Well, first we used moonlight, which is not what these data weren't intended to be used for in this way. And he also came up with a result which wasn't too far away from what we know now. That's pretty remarkable in my book. And then there were a few other contributions, and I'm not saying that they weren't just as good, but there were a few at the start of the 20th century. And then we had a big gap for one reason or another. And then came a guy called Guy Callender, and he was a steam engineer. So all of these people weren't climate scientists. They didn't have climate scientists like we do today. He was just interested in this. And he studied the artificial production of CO2 and its influence on climate. And he published a number of papers. And this is some plots from his paper in 1938. And what he was showing, this is CO2 in parts per 10,000 by volume. So this is basically ppm. So this is 300 ppm. This is where we are today, roughly 400 ppm. And what he plotted was the change in temperature. So this is the temperature change. This is where he was at that point. So he was around about 310 ppm. So as CO2 increased in the atmosphere, temperature increased. And as we went back in time, when CO2 was a bit lower, there was a reduction in temperature. So he was making this argument, and it's not clear to me where he got this data from, and in fact all the reviewer comments from this paper are in the back. So there's huge amounts of skepticism about the quality and the origin of this data. The other thing he said he was showing was that he was charted an increase in temperature as we started the 20th century. We now know this is probably largely due to natural variability, but what he based on was an average of temperature data from Edinburgh, Oxford, and Copenhagen. He also showed that there was a similar trend in temperature from New York State. But again, there was tremendous skepticism, some of it reasonable, some of it less so. One of them was, well, this CO2, these huge amounts of CO2 in the atmosphere, the ocean, we know the ocean's going to take it up, why can't it take up more and more? There's a huge expanse of ocean. And we didn't have that much data, so he was argued that the surface ocean, I don't know if you know, there's the surface ocean, very thin layer on top, that mixes rather quickly. That will saturate, surely. And so the mixing from the surface ocean to the deeper ocean happens on a much longer time scale. But apart from that, apart from just simple arguments like that, he couldn't really rebut many of the criticisms he faced. And the other thing he was criticised for was that he didn't include convection. He only included radiation as a way of shuttling this energy and heat through the atmosphere. But this is an example, actually all of these are all these scientists before are examples of scientists who used ingenuity and logic to try and push their arguments together, forward. Because we knew that there was a relationship here, and they just tried to develop theory. And if they hadn't come along and done this, we would be a lot further behind than we are today in our understanding of atmospheric CO2. Now, the 1950s, strangely, was a really, well, I actually do know why it was an important era for CO2, and this is partly due to the Cold War. There's lots of activity in carbon isotopes and radioisotope. Gilbert Place did some pioneering experiments here. He calculated the heating, the top of the atmosphere heating due to CO2. So he was able to predict CO2 concentrations for the 20th century and their effect on surface temperature. So given the trend he saw in the 50s, he increased that trend and he reproduced the surface temperature remarkably accurately. The second set of people I thought was definitely worthy of mention is Rogerravel and Hans Suess. And they showed that seawater chemistry prevented unlimited absorption of atmospheric CO2. This was a criticism that just haunted many of the other people. And it was a conservation of alkalinity. So CO2 increases the acidity of the ocean, and there's a limit to be able to take up the CO2. And then we have Charles Keeling. This is not in 1957, but in 1957 he looked much younger. Again, another example of a great person that had, who was able to use his knowledge of measurements and developed a very accurate and precise measurement of CO2. And he's the one that started off the CO2 measurements at Mauna Loa during the International Geophysical Year. Before that, we didn't really have atmospheric CO2 measurements for any extended period of time. So the 1950s really was an important decade. So this is, again, we're just Mauna Loa here. This is an early paper back in 1960. The first data he showed was here, this black line here. The rest, these are aircraft data. So he was able to chart a seasonal cycle in atmospheric CO2. So there's two big discoveries here. One of them was we saw this natural seasonal breathing of the planet, this land-based vegetation, predominantly land-based vegetation, that had not been seen before. And the other important thing is, particularly for papers that came after this one, the time series got much longer, was that we were able to show that the rise in atmospheric CO2, we were able to show there was a relationship between human emissions and the Earth's atmosphere. Before, we'd assumed the atmosphere was so large and the oceans were so large, we wouldn't ever make an impact. But we did, and these data were the first to show this. So this is the CO2. This is the plot I showed you earlier. And so we can see it quite clearly. So he measured just I think up to about 1979, and then the federal government took over. But a huge amount of effort went into measuring this, maintaining a record. That's typically of science. We don't typically have long-term records of many gases in it before then, and certainly now there's a lot of gaps in our understanding of trace gases. So how do we know what we know now? There's a lot. So this is where I've skipped over a number of decades. There's a huge amounts of measurements, technological advances, computing resources that I've skipped over. What we have are computer models which now take in information from measurements, very detailed measurements of tree growth and flux measurements over canopies. And we were able to, so these models, computer models, are great ways to extrapolate data. So they can relate from one region to another using equations, biology, chemistry, physics, everything. And what I'm showing you here is the gross primary production, essentially the chemical conversion to biomass. So this is grams per carbon per meter squared per year. So this is the ability, essentially the ability to extract CO2 and convert it to biomass. And most of where we think it is in the tropics. So fossil fuel emissions, we know where the power plants are, and these are dotted around the world. This is an example of the NOAA network that I showed you before. Mauna Loa is up here. You can see it's been extended now over a number of years. But what you'll notice is that most of the data is in the Northern Hemisphere. Most of it's over Europe and North America. Very few data points are in the tropics. And that's not because we're not interested in the tropics, because we are. We're not here because these are harsh environments to work in. They're very difficult to work in and maintain a high quality record. Just simply, and it's also important, it's also difficult to relate a 1 point measurement in the middle of the Amazon basin to the larger basin. But what we've done over decades is try to pull together everything we know about the carbon cycle. The cycle is everything's all connected together. So here is a recent depiction of what the carbon budget is. So this is basically the numbers attached to all these inputs and outputs to the atmosphere. So here I'm introducing a new unit. So this is what we call a petagram. So every time you see a ppm increase in the global atmosphere, that amounts to about 2 petagrams. A petagram is 10 to the power of 15 grams, or twice the weight of the mass of the human population. So every time you see a ppm increase, you're actually seeing 4 times the mass of the human population being thrown up into the atmosphere in terms of carbon. So the numbers we've got here, so we have fossil fuel, that's 8.3 plus or minus 4. So that plus or minus means the uncertainty. So we know pretty much what the input from fossil fuel and cement production are. We know the atmospheric growth rate. We've seen that data. It's fairly accurate. We have a fairly good understanding of how much that's going up. Land use change, so deforestation, burning, so go from forest to pasture, or just ripping down forests. That's about 1 plus or minus a half. So there's a 50% uncertainty associated with that number. The ocean sink, we get from measurements, it's about 2.5. And what's left, it's important to realize that what's left is about 2.6 petagrams. And we only really get that from a residual from the balancing this budget. So let's put this in terms of time. So this is the same data, CO2 flux in petagrams per year as a function of year. These are the emissions into the atmosphere, and this is the sinks. This is what's taken out that CO2 that we've emitted from fossil fuels. So the grey is fossil fuels and cement production. This beige colour is land use change. This is light blue is the CO2 that remains in the atmosphere. The green is the land sink, how much is taken up by the land, and this blue is how much is taken up by the ocean. So over this period, 2002 to 2011, fossil fuel emissions represent about 90% of the emissions that go into the atmosphere, with about the remaining 10 coming from land use change. The atmosphere retains about 46%, give or take. The ocean takes up the additional 26%, and then the balance of that budget, 28%, is the land estimate residual. Now the point is, we don't know where this uptake is. That's why we have to take the residual. We don't know. It's one of the remaining puzzles of the carbon cycle. So let me just tell you a little bit more about the carbon, this land sink estimate here. So this is some work I'm showing you from James Barlow, a PhD student of mine. So this is the data. This is the growth rate. This is the amount of CO2 that is increased per year. This is the net carbon flux to the atmosphere, and the colours. So this is a function. This is a latitude and growth rate. The colours are blue, the 1980s, red, the 1990s, and black is the noughties. So blue, you can see that the growth rate of CO2 is 1.6 ppm per year. So CO2 increases 1 ppm per year in the southern hemisphere. In the northern hemisphere, it's much higher. In the 1990s, it's actually pretty similar. In fact, in some cases, much lower, especially in the northern hemisphere. And that's due to the collapse of the Soviet Union. That's a big decrease due to the collapse. And then when we get back to the noughties, you can see this is ramped back, right back up. And now we're close to increase. Every year, we increase the CO2 in the atmosphere by about 2 ppm, roughly. Now, what we can do to this, which is really nice, is that we can actually subtract the fossil fuel. Because we know the fossil fuel reasonably well, we think, you can subtract that from the growth rate, and what you end up with is the natural carbon flux to the atmosphere. Now we see a very different picture. So now in the 80s, we saw a drawdown, a reduction of CO2 growth rate of about 1.7 ppm, and a bit lower in the northern hemisphere. The 1990s we've got an increased sink, so that's about 2.2, 2.3. And the last decade is 2.4, 2.3. So somehow this sink is reacting to CO2. You know, CO2 is increasing, but the growth rate is the land biosphere, or the ocean, is taking up more and more CO2. Another way to look at this is what we call the airborne fraction, and this is the percentage of the CO2 that remains in the atmosphere. And over the past 50 years, it's approximately constant. So 44% of the emitted CO2 in the atmosphere remains in the atmosphere. So if you figure the CO2 is increasing, that's quite impressive that something is responding and just taking up a bit more carbon each year, a bit more CO2 from the atmosphere. So let's see if we can tease apart get some more insight into this CO2 data. So this is what I've done is a schematic of the CO2 curve from Mauna Loa. It could be any one. This is CO2 and ppm, as we've seen before, and this is time. I've taken out the linear increase due to fossil fuel combustion, so now we're left with what we think is the natural cycle in the time series. Now the height between the peak and the trough, this is the peak here and the maximum of any one part of the seasonal cycle, and the trough, which is the minimum, that distance is the amplitude. And that amplitude is a measure of the biological activity of the land and ocean biosphere. And we'll look at the max. So this max from this line here, because we've subtracted, say this is 0. So this is a max, min. So we'll look at those two distances as well. more work from James. Annual amplitude trend. The amplitude trend, so this is the increase in the amplitude, that distance with the max and the min per year over a sort of at least 20 years. And you see most of those values, the big black blobs, they're the ones that are significant. There's the ones we're most sure of that there is a positive or negative trend in the amplitude. So you can see there's quite a large increase per year in the Northern Hemisphere. So something is increasing at amplitude. So, I mean, if we go back to this, is it the maximum? Is it increasing? Because we're only, at the moment, I've just showed you the amplitudes. Is it the max or is it the min that's increasing? And it turns out they're both increasing. So the maximum's getting bigger and the minimum's getting lower. So it's getting much smaller, more negative. And so what I'm showing you here is the maximum anomaly and the minimum anomaly. So the anomaly is the distance from some baseline. The colours denote the years. So in the 1980s, we're out here. And in the 2010, we're in the reds. And these are data points from 60 degrees north onwards. And what this is showing is that we go from the 1980s to present day, we are seeing this progressive, the minimum's getting smaller, the maximum's getting much larger. But the minimum's growing faster than the maximum. So this drawdown is increasing more negative, slightly faster than this is getting higher. And this balance is critical because as long as the minimum is larger than the maximum, we have more uptake with time. But it's a fine balance. I mean, there's not much in it, at all. A little perturbation to the maxima, and there's going to be a whole lot more CO2 in the atmosphere because there's going to be less uptake. Another way to look at this data is to look at the distance. So this is the CO2 curve again. And as the CO2 goes down from the maxima to the minima, it crosses this line, which is just some arbitrary line, which is set to 0. Downward 0 crossing point. And then we have, as it goes from the minima to the maxima, hits this line again. That's the upward 0 crossing point time. That distance between those points is an indication of the growing season, the length of the growing season. It's not the growing season, but it's an indication of. And what that big plot of time series of CO2 didn't show is those changes. You can see it changing from year to year. And what you find is that the start and the end of the growing is a complicated plot, and I can explain it. Look, so the downward 0 crossing point anomalies. Remember, this anomaly is just relative to some baseline, and this is the upward 0 crossing point anomaly. And so this is in the tropics, and this is the high latitudes, and we go from 1980s. The 1980s in blue. And more recent years are in the oranges and reds. And we're seeing this progressive. So it's a quadrant. So the upward 0 crossing, if the upwards getting earlier and the downwards getting earlier. So we're moving from this positive. So in this quadrant here, we're moving downwards. The 0 crossing is getting earlier, and the upward 0 anomaly crossing point is getting earlier. And there seem to be some synchronicity. There seems to be some progressive march towards an earlier growing season and the start of the growing season and the end of the growing season. Now, the start of the growing season, we think we understand. So increases in temperature, that promotes growth at start, an earlier growing season. But the end, we just don't know. This is an active science question. We don't know. So there's lots of little problems like this. You can see that there's some really cool movement. So it's just really nice, and the data really nicely supports some really synchronicity in the movement. But I have no idea what this is. This is just an example of science in action. So that's the data. So more sophisticated analysis requires computer models. Nowadays, it's very difficult to do lots and lots of science without these computer models. And in this example, this is a figure provided by Liang Feng. We're using this tool to estimate fluxes of CO2. So this is a very sophisticated model. It's driven by NASA weather prediction data. So you can see this is a 1 month in 2008, and you can see that these filaments of CO2 being wafted around the world. And you can see that the CO2 from one region can affect other regions. This is true for many gases. You can see it's quite hypnotic to watch this. You can see blobs of high CO2 wafting over, and you can see periods of uptake where you see these blues draw down from the surface. And these computational tools embody everything we know about the science of CO2, or at least we try to pack in as much stuff as we can. Now, the way we estimate CO2 from this, the idea is relatively simple. So we start off, this is the real world. So we have a source, factory, fire, land, the vegetation, this is the ocean. And they have a positive plume or so this negative plume is the uptake of CO2. So you might get depleted ozone plume in the atmosphere. And they fly around, aircraft, satellites, land-based surface observations, and we measure these plumes. So we know what the values are. These are the observations. And they have some uncertainty, but we know what they are. Now the model, this is the model world. So the model, we have some caricature of the source. So we have some factory or a tree, and we emit a certain amount, which we know is roughly right. And we can fly around our model. So that's a 4D field. You see it's quite detailed. We can fly around the aircraft. We can fly around with the satellites. And then we compare the model with the data. And what we do, we decrease that distance between the model and observations. We try to make the model match the observations, taking into account uncertainties of the model and the data. So we just basically increase or decrease until you get that match. And that's pretty much it. It's a lot of detail in there I've missed out, but essentially a least squares fit of the model to the data. And what you end up with is something quite profound. It's like the emissions from huge continents. So what I'm showing you here is an estimate. It's work by Liang Feng. So what we have here is petagrams of carbon per year. It's 2003, 4, 5, 6. These are the northern hemisphere continents, the tropical continents, and the southern continents. The black line is what we start off with, and the line you can see here, that's the uncertainty we have about these emissions. And the blue and the red line, just don't worry about the difference between these two, but pick on one of them. And the uncertainty on those values, that's what we end up with, by the way. The grey line is what we end up with, the uncertainty of what we end up with, that's what I should say. So for the northern continents, and in some respect the southern continents, you can see there's some distance between what we started off with and what we ended up with. So we've learnt something by fitting the model to some data. In this case, the data is surface observations of CO2 around the world, that surface network I showed you earlier. So we've learnt something, it's different. And it has quite large implications in terms of the budgets. But for the tropics, we don't have much data. So you can see that we haven't learnt a great deal. That grey envelope around the blues and the reds are very similar in magnitude to that black line. So that means we haven't learnt a great deal. And that poses a real problem for us because we need to learn more about that because that's where we think most of the CO2 is taken up. So one of the big hopes for our community, and stress is one of them, there's other activities that are going to try and improve the situation as well, is the launch of satellites. And for those who can't see, this is the greenhouse gases observing satellite. It was a Japanese instrument that was launched in 2009. So Edinburgh University are involved with this. It's a big international collaboration. There's also a NASA instrument that was launched soon afterwards but failed and crashed, which is going to be launched next year. So they've rebuilt it and they're going to launch the same next year. And what this measures is CO2 and methane. Now, the good thing about satellites is that it's frequent. They measure around the Earth. They're indiscriminate. They don't care where they measure. There's no problems with harsh environments, the tropics. They just don't care. Right? So that's good. But the challenge is that what they measure, they can't measure in clouds. So you can imagine the tropics is full of clouds or fires producing particles in the atmosphere. That has implications for interpreting data. And the other problem is that it produces a column. And I won't dwell on this problem, but the fact is that it measures a column. This is a function of altitude, and this is the sensitivity of the instrument to changes in the vertical. So the blue line says that we're most sensitive to CO2 in the lowest 10 kilometers and most sensitive to really the lowest atmosphere. And it's very difficult to interpret that without the models. The computer models play a big role here. The way the satellites measure CO2 is that they sit around about 600 to 700 kilometers above the Earth, and they stare at the Earth's surface. And what they measure is the solar backscatter radiation from 600 to 700 kilometers. So these data are some of the most precise measurements of the Earth's atmosphere that we have today. And what they measure are these absorption spectra. I don't want to go into these too much, but basically this is the Earth's spectra in a particular wavelength region. And in that complicated structure here are signatures of CO2 absorption. So they're able to pick out this very fine structure, measure these changes. This is what you end up with. This is the Gosak data. And these are 3 models. This is the one based in Edinburgh. This is a US model, and this is a French model. And what I'm showing you is, I think, 2010, 2011, so it's 2009. You can see during the summer months, which are about now, you see drawdown in the middle of, summer now, yeah, so drawdown here in the blues. Winter time, we have less data because we need the sun as the source of information. So in the northern hemisphere winter, you can see there's less data here. And during the summer, that fills in. You can see the drawdown. And the models do a real remarkable job. The fact that there's any agreement between the model and the data is remarkable here. But you can see that they all agree reasonably well. So this is the thing that's keeping us busy now, to try and take this data and to estimate fluxes from this data. I'm not going to show you that. In terms of the future, this is what I said I didn't have. This is the only slide I have. This is what I'm showing you here is the fossil fuel cement production, basically the anthropogenic emissions of CO2 as a function of time. And what the IPCC use is what we call the representative concentration pathways, and define radiative forcing and the surface warming. And these are 4 representative concentration pathways they use, which embody a variety of different assumptions about socioeconomics, political decisions, and how economies all work together. So they go from the incredibly optimistic to the worst case scenario. So each one of these, so this is the best case scenario, we might lead to a warming of about under 2 degrees. This is the one we're supposedly aiming for, which is about 2 to 3 degrees, end up with 2 to 3 degree warming in 2100. And this is the worst case scenario, which is going to lead to about 4 to 6 degree warming. Fossil fuel emissions up until this, about 2 years ago, which are given in the black dots here, about 2012, were exceeding the worst case scenario. I think they've dipped now with the economic decline, but it's not far from the worst case scenario. What we're trying to do is trying to keep it below 2 degrees Celsius, because be above 2 degrees Celsius, we just don't know what's going to happen. We don't even know what's going to happen at 2 degrees Celsius, to be honest with you. It's quite difficult. It's a complex, the Earth system is a very complex system, so predicting changes that are going to come about from quick, rapid increases in temperature is very difficult to predict. If you want to know more, there's a link here you can follow, and it will give you a comprehensive description of these RCPs. But one of the big things is to try and encourage those emissions to go down. Okay, so the first thing we need to do is quantify those emissions properly with uncertainty, and to understand where those emissions are coming from. And this is the example that I wanted to raise towards the end. This is an example of a project which is going to quantify the greenhouse gas emissions of the UK. It's called GAGE. And it's in response, it's a funded project by the Natural Environmental Research Council, and it's really in response to these climate change acts. So the UK has a Climate Change Act, which aims to reduce greenhouse gas emissions by at least 80% by 2050 relative to 1990. The Scottish Climate Change Act, 2009, has similar emission goals, has some interim targets as well, which are quite useful. But how do we know we've actually reached those targets? We don't know. We can guess, but we don't know. I'll tell you why. Because CO2 in the UK represents about 85% of greenhouse gases. CO2, methane, and N2O are really the 3 dominant greenhouse gases of the UK. These are the ones that we're going to be trying to quantify. This number is probably highly uncertain. You can see that they're very, very different in nature. They come from different places. So CO2 is energy supply, road transport, business, and residential. Methane, agriculture, waste, so landfills, and there's a smaller contribution from the energy sector. N2O, or nitrous oxide, most of that comes from agriculture. You can see there's a whole range of different sources that we have to quantify in different ways. So which one do we reduce? How do we know which one's more accurate? How do we know that these emissions are accurate, particularly the agriculture and land and waste? The energy supply, are the companies really telling us what they're burning? I don't know. Perhaps they are, perhaps they don't, but they don't tell us. I don't know. But having a measurement of CO2 and the other gases is really important. That's a ground truth of these emissions. And this is an example of, this is what we're trying to build right now. So the Department of Energy and Climate Change have a site up in Angus. It was previously run by the University of Edinburgh. They have a site at Tacklestone, which is at East Anglia, and Ridge Hill. So this has been run for the last couple of months. And the idea behind these sites, they're all on telecommunication towers. And what they have is clear, basically tubing that sucks in air at the top of the telecommunication towers, or a variety of different heights in this tower, and sucks it down and measures the CO2 in the atmosphere that way. And DEC, Department of Energy and Climate Change, put them there to comment on the greenhouse gas budgets of the devolved administration. So you can see it's on the boundary of Wales. This is one for England, this is for Scotland. What we've done is add some more. So we have one at Bilsdale, we have one in the middle of London, BT, we have Heathfield, which is downwind of London, and we also support with a Mace Head's a baseline. So that's basically air coming from North America over the Atlantic. So it's relatively fresh. It's not just from North America, but it's coming from sorts of clean air sectors. So on top of that, we've got something that's isotopes. So isotopes gives us a slightly different flavours of the carbon dioxide and methane, which tell us a bit more about where the CO2 and the other gases come from, the anthropogenic sources. We have the atmospheric research aircraft, which flies basically an EasyJet with all the seats ripped out and lots of atmospheric instrumentation thrown in. And there's lots of pipe inlets, so when it's flying along, it just sucks in air and you can see what's going on in the atmosphere. And that will be flying up and down and across the UK over the next year. We also have a ferry that goes from Rosyth to Zeebrugge, and that will be running from the end of this year for 18 months. And we have the satellite observations. So it's quite complicated to put together a greenhouse gas budget, and it really brings together the community in different ways. So one of the things we've got to do now is, well, once we have all the data together, we bring all these data together in terms of all the models. So we go from the global models, which I showed you that really hypnotic movie of CO2 moving around, all the way down to, this is a large scale, all the way down to a kilometre scale modelling. So we're starting to look at point sources from factories and landfills. And one of the most important objectives of this research is to quantify not just the emissions, but also the uncertainty. To try, because a measurement without uncertainty is of questionable use. Okay, so it's important to know that. So we put together all these models and we're all fitting lots of models to the data. Different models are different assumptions. So you end up with lots of different results, but we're looking at the range of different model results you get, and that's a way of looking at the estimates we get. So here I want to, this is the one last, there's a movie here which is pretty much summarizes what I've been talking about. It comes from Noah. Okay, so this is really important. This is a really great movie, so I'm glad we could manage to get this on. So what we're seeing here is the atmospheric CO2, and you're missing out the southern hemisphere. That's less interesting anyway. So you can see it's up and down as we go through the year. And this is collecting the time series that we've seen with the Keeling curve. Let me just speed it up a moment. But so this is what's showing the up and down. The red line is the Mauna Loa. Where are we? What's this going to take? So you can see it's going up and down. And as we get to about 2000, so we read some landmark dates here. See the number of points are increasing and decreasing. This is the baseline, this is going up and up. We've reached 300 ppm now, this is in October 1989. If you look for 97, this is 2001 now, 2002, 2003, you can see that it's going up and up and up and up and up. You can see this is basically some of this is the breathing, some of it's anomalous events like fires can sometimes perturb the CO2 growth rate in a dramatic way. Now once we get to about, here we are, so now we've extended this down to 1959, 58 with Charles Keeling's data. This follows on quite nicely. And now what we're going to do is going to put all the ice, which is you've lost now, so all the ice age data. So CO2 was up here at this point. And now we're going to see that it go back 10,000 years, 100,000 years, and you can see that you can start to see the glacials. I think we're about 100,000. Start to see massive increase. And this is the glacial and interglacial periods. So that's just to put the context, the amount of, so we're up here, we're sort of up here. So we're the highest it's ever been for 800,000 years. And the speed at which we got there is quite impressive. All right, let's go back to this. Okay, so back to this. So, let's see. So we just finish off with some science lessons here. I would argue that atmospheric CO2 is probably the most honest way of observing changes in CO2, the surface sources and sinks. Everything that you emit into the atmosphere has a signature in the atmosphere. And so the trick is to interpret those variations in atmospheric CO2. We've seen there's a lot of really accomplished scientists tackle some big puzzles without any data, very few data, without the luxury of large-scale computing. Now we have some really large outstanding puzzles still to solve. And we do have that luxury of computing. We do have that luxury of measurements. And solving some of these big problems are really urgent, particularly that missing uptake. We can't reduce emissions if we don't know don't know the origin. It's just common sense. And we don't know the robustness of what we think is the biological sink. It might saturate, it might fall over one day, and if we don't solve it, that's going to be a catastrophe for atmospheric CO2 and surface warming. There's going to be what could lead to a runaway effect. That's a very pessimistic way, of viewing that, but it's something that we need to start thinking about. I just want to finish off with this slide just to say thank you to the CO2 molecules, Doug Finch, Kathleen Allen, Emma Noland, and also the artistic director, Robin Butler. So thank you very much.
Malcolm Oliver, how quick is the reaction of the atmospheric temperature to increases in CO2? I'm thinking particularly, you see occasionally references to some lake in Africa which is supposed to have mega amounts or peta amounts of carbon dioxide trapped at the bottom, which might be released very quickly. What would be the impact of that on global temperatures, in a week, in a year, or whatever?
That's a great question. I don't know the timescales at which, if you perturb CO2 with great big impulse, how quickly it could change temperature. I'm sorry. It wouldn't be instantaneous.
My name's Norman Dalglish. If I followed correctly, you put out one of the charts from the pioneers showing an increase in CO2 in the early 20th century, and you referred to that as being a natural variation, but then you haven't sort of referred to that in context of the Mauna Loa record. Could you just say a little bit about that?
The Mauna Loa record starts in 1959. The warming that we saw was the start of the 20th century.
But if you dismissed a chart showing an increase as natural variation, surely you need to address that fact. I'm not asking as a skeptic, but you need to address that fact when you put up another chart showing an increase and you say, oh, this is different.
The only thing I can counter with is that the CO2 back then was much smaller. It was increasing at a much, much smaller rate than it is today. I don't have a plot that shows you the natural variability, but that's more natural variability than the anthropogenic at that point.
I guess if I rephrase my question is, what are the sources of the natural variation then that drove the early 20th century change?
I'm not sure of the exact one, but there's a lot of other sources. Variations in solar radiation. That's one thing that could change it. So it's just not CO2. I think that's the message that I was trying to get across.
Could you just briefly touch on feedback issues when it comes to CO2 and how those would also contribute?
Have you got anything in mind?
Well, for example, like the release of captured CO2 with the tundra, or the shrinking of the glaciers, and how that would, these various other contributing factors to greenhouse gas that are related to warming.
Well, there's a lot of feedback mechanisms. Their importance is going to. I'm not sure where you're coming from, but there's a paper back a few years ago where they were looking at tipping elements. And so there's these feedbacks, and they can get so strong that they can just continue forever. They sort of runaway effect. I don't think so. We looked at some of these effects, And there's ways to look at this in the data to see if there is an evidence of this, and there isn't. There doesn't seem to be any evidence of runaway effects right now. That's not to say that won't happen, it's just to say that there isn't. So the tundra one that you're talking about involves methane and CO2. So methane is also a greenhouse gas effect. It's more potent per molar basis. And so by exposing more of the tundra, if you're warming it up, exposing more of the vegetation underneath, it warms it up, produces methane, warms it up. So you get a sort of a feedback there. But I mean, there's a whole range of these feedbacks that possibly could happen. I think there's just a huge amount of uncertainty, and a lot of work has to go into trying to quantify at what point we think these are going to be self-sustaining. That's all I can say at that point. Just a lot of uncertainty. We don't really know. Huge amount. It's a lot. I mean, if you look at these Earth, the model calculations, then no one's going to stick their hand up and say this is what's going to happen.
My name is Maurice Bradley. I'm not an expert in this field. I'd like to ask you to clarify a bit more your final slide with the question that was on, which was, we don't know where the emissions are coming from. I think you've made it clear that we don't know some of the sources of emissions, but we do know that the primary source of carbon dioxide is burning fossil fuels. Would it not be a direct way of measuring how much of a problem we've got to measure directly the sources of burning fossil fuels, or even better, the extraction process, and then apply the measures to control that?
We know where the fossil fuel emissions are occurring, and we think that we know roughly how much is being emitted to the atmosphere. And this is typically based on what gets consumed. And they make a calculation between what gets consumed and what goes into the atmosphere. Now, I'm not really sure of your last point about what the measures we can reduce fossil fuel emissions. What I was really getting at here was fossil fuel emissions is just one aspect of greenhouse gas emissions. And while I'm for reducing fossil fuel emissions, we also need to know, you saw that was one component of the budget. We need to know the other components as well. So I'm not saying that I'm going to ignore fossil fuel emissions. I'm just trying to think, well, okay, so we're relying on these biological sinks to basically vacuum up the CO2 that's emitted by fossil fuel. My role as a scientist is to try and figure out where the CO2 is going. I think I'm more interested in that at this point, and leave it to the politicians to make reductions of fossil fuel emissions.
Further on that question, it seems to me that despite all the talk about targets, there isn't even a credible plan about how you would go about in reorganizing society to achieve a significant reduction in CO2 emissions. I think there is a massive vacuum in that area.
I agree. I think there's a point at which we are going to have to rethink how we live our lives. Because if you look at that uncertain futures, the longer we leave it, the bigger change that we're going to have to make. I think, where is it? Went past it, okay. So that's assuming that we're going to go up a little bit, perhaps 2025, and then we're going to make, I mean, it's for me, that is pretty unrealistic. As a non-scientist, just a man on the street, it seems really unrealistic. So we're going to have to really think how we live. Yes, I agree.
When you were going through the timeline of all the different people and how they contributed and what they kind of put into the theory of fixed air and CO2 emissions, did they do that with a view to, were they seeing the longer picture of how that was dangerous and we needed to reduce? At what point did someone actually start saying this could be a problem and we need to start fixing it?
It was Guy Callender that made that connection between present day temperatures and CO2. So the previous, the impetus for the science was really about learning about the ice ages, trying to figure out going from glacial to interglacial. So Guy, I mean, all these scientists, I mean, they inadvertently helped understand the climate change problem, but that wasn't their, they didn't have an agenda. And nor did Guy Callender. I mean, he was widely, there's lots of skepticism around there from a scientific point of view. And he wasn't really interested in climate change. I mean, in fact, I think some of the comments were that it wouldn't be such a bad thing to warm up few degrees, particularly over the UK. So they didn't have that in mind. So that's important to keep in mind when these early pioneers, they didn't really have a whole climate change thing at all. It wasn't until Gilbert Place in the 1950s when they suddenly thought that, hey, this might be a problem.
What's your opinion of what the stable point will be if we assume we'll take the worst case scenario, saying that looks like that's where we're going? What do you think it'll stable out at, or do you think there'll be another sort of bifurcation when we reach the top?
Okay, so I'm a scientist, not a fortune teller, but I mean that's a difficult question, right? I mean, even so beyond 2100, you want me to predict?
Just what your opinion is. What looks
The end of the world.
it's pretty ominous.
I wouldn't even want to say anything about that. In fact, I'm a scientist that would rather limit to this. I don't really like going out to 2100. I don't find it particularly useful because the thing is, we're all human, right? We don't care what's going to happen next week, let alone 10 years' time, 20 years' time, 100 years' time. Who cares? So I want to make sure that we study now and we study next decade, because that has more influence on what we do now. We'll just put it back 2050. Who cares what we do now, right? Yeah. I think that's really important. So I would say that I would hold back, and I would probably spend much more of my effort in looking at these coming decades rather than even talk about what's going to happen beyond 2100. I'm sorry, it doesn't answer your question, but that's my philosophy on this one.
My name's Aaron Thierry. I was wondering, so you're using this graph to say, look, it's very unlikely we're going to keep to our carbon budget, which would keep us below 2 degrees C of warming. So do you think that we can use our understanding of the biological sinks to try and draw down the CO2, say if we are overshooting to try and take it back out of the atmosphere after we put it in there? And what's our understanding of that, considering there's so much uncertainty currently?
I think that's a great idea. I mean, if we can find out where it is and we can look at the nature and the durability of this sink, then yeah, if we can come up with an artificial way of doing that, that'd be great. We're not at that stage right now. Some technologies might be at that stage, but none that I know of right now. And I think that is also an aspect to this guy's question. If we just say, well, we'll find technology in 20 years' time to take out more CO2, that's really just you need to figure out, it's not really addressing the question that we have right now. That's all putting it off. So it's a good idea. If we can find it, we'll do it, but I don't rely on it.
It's related to what you were saying earlier about the feedbacks. You were saying that there's an increasing rate that the CO2 is sunk at as the production's increased. Has there been any indication that that's changing as the amount that we're producing increases, as in that the amount that the Earth is able to absorb is decreasing?
What I showed was that as atmospheric CO2 is increasing, the percentage of the CO2 that remains in the atmosphere is the same. So something is taking up more and more carbon. In the percentage terms, it's reasonably constant. But we know CO2 is increasing, so that means it's taking up. There's no evidence that it's slowing down. But there's no reason why it won't saturate. We don't know really the nature of this uptake right now. Is that what you were asking?
Yes.
Bilbai, your chart with calendar suggested that the effect of CO2 on temperature was logarithmic. If you take the logarithm of 280, the previous pre-industrial, and you take the log of 560, the doubling, to give you the sensitivity, we're about halfway, because the logarithm of 400 is about spot on. Since 280, over the Hadkrat 4 only shows 3/4 of a degree warming. Why should we get any more warming for the second half of this logarithmic curve?
That's a good question. The only way I can answer this is let's see. I don't really know how to answer this one. It's a good question. there'll be processes going on in the Earth system which are compensating for this fact. I mean, the curve that Callender came up with was preliminary, right? I mean, we just don't know what the we didn't know at that point what the temperature increase was and how it increased. We know a bit better now. And there'll be blips in the Earth system. So I mean, if you're worried about changes in the decadal, so if we plotted the real CO2 to temperature curve, I'd imagine there'd be a lot of blips. It wouldn't be as smooth as that, because there's a lot more things going on in the Earth system than just CO2 and temperature. So I think that while I can't answer your question properly, I think that you just really need to realise there's a lot of competing processes in the system that could slow it down or speed it up. Sorry.
But if Callender's curve is right, we're only going to get another 3/4 of a degree.
Oh, is that what your point was? I'm sorry.
So
well, I mean,
sensitivity
there was a
of
lot of
1.5 degrees and not 6, like you're saying.
Oh, well, hang on. So okay, now I understand your question. Sorry. Okay, so Callender it was very simplistic the way he was coming up with. He didn't take into account. He was really looking at a very sort of reasonably local level and looking at CO2 values which are highly dubious. But the point I wanted to make with Guy Callender, he was really looking forward to the science. I mean, a lot of science was, what he ended up was wrong, but the science, the ideas were right. The RCPs was what you were showing, the uncertain futures. I mean, you're talking about global scales, much grander emissions, huge amounts of emissions going on here. Difference, like he didn't know about deforestation. From satellite observations, we know all these things happening on very large scales. He didn't know that. We didn't know the extent of burning and fossil fuel combustion. We didn't consume as much as we did back in the 30s and 40s. Things have gone up dramatically. I would say that his curve is completely wrong in that sense, in terms of. So I'd be careful what you transferring how that plot from Callender and what we know today. Sorry, that should answer your question.
One final question. Yes, great. Thank you.
Hiya. I want to ask, some of the scenarios indicate that with the opening of Arctic waters for shipping, it may actually mean some significant reduction in global CO2 emissions, but it's going to increase the local climate forcing or local emissions. And I want to ask, in relation to that, how much does the intake or uptake of CO2 differ in relation to temperature and the already existent pollution in the air, in the atmosphere?
So could you repeat that question? That was quite a long question.
Like how? Sorry.
It's okay.
Because in the Arctic area, there's not a lot of pollution there right now in the atmosphere.
There's a lot of pollution in the Arctic.
Oh.
Huge amounts. Okay. It gets transported there. There's all kinds of material that are deposited onto the snow that affect the surface albedo. So, for instance, there was an aircraft campaign by NASA a few years ago, and they were flying over this region, and they were looking at black carbon. And black carbon, when it's deposited onto the ice surface, changes the albedo. It increases the warming. And the emissions, the clouds, feedbacks that we have, these all affect the warming. So I wouldn't say the Arctic is pristine. In fact, sadly enough, I don't think there is very many pristine places on the planet left.
But does the temperature actually influence the uptake of CO2? Or does it really
The temperature
matter?
of the ocean, yes. So colder oceans would take up more CO2 than warmer oceans. It's the same as if you warm a can of Coke. All the gas comes out, right? It's the same kind of idea. It absorbs more gas when it's cooler. So it would have a feedback, yes.
Well, I think we should call the evening to an end, but I would like to offer a vote of thanks to our speaker, Paul Palmer. So he's taken us from the early days of these gentlemen scientists, yes, they were all men back then, who were researching this out of interest, noticing, discovering CO2, starting to hypothesize that it might have some relevance to past climate change, so the origin of the ice ages. And now we've come forward, and Paul's clearly shown us that carbon dioxide in the atmosphere represents a very serious and significant issue for humanity in terms of deciding on how it's going to progress, the decisions it's going to make about the way in which it generates energy, the carbon dioxide emissions it makes to the atmosphere. But fully understanding what the future is very complex and relies on a whole host of different inputs of research. And so Paul's illustrated that physics and using Earth observation is going to be a really powerful way for us to assess this in terms of understanding the current sources and sinks. But also we are going to have to integrate that in with social science, with economics and business to come up with any realistic solutions to these kind of pressing issues. So we've gone from kind of halcyon days when gentlemen scientists were doing this for pleasure to a time when actually it's very important that we engage as a community around a whole range of different axes to understand what the nature of the issue is and what the potential solutions are. So I'd like to thank Paul very much for his insights on this.
This production is brought to you by the University of Edinburgh.